Okay, in this video we're going to look at the chain rule as a method of differentiating composite functions. Before we look at the chain rule, we're going to differentiate this composite function, kind of a brute force method where we're simply going to expand this x squared minus 4 to the power of 3, and we'll differentiate this with the power rule, of course. And then we'll tinker around, play around with our derivative and see if we can look for a shortcut. And of course that shortcut is something called the chain rule. And I think this will also allow you to appreciate, I guess, how effective the chain rule is, because it means you don't have to do what we're about to do here. So binomial expansion here, obviously, so it's going to be x squared, the first thing in this that we're cubing, to the power of 3. And then we'll have a binomial coefficient, 3 choose 1 from Pascal's triangle. And then we'll have 2 of these x squares multiplied in a single minus 4. 3 choose 2, our next number in Pascal's triangle. We have x squared now once and minus 4 twice, and then finally minus 4 to the power of 3. So that's not too bad since we're dealing with something cubed there. But of course, if that was a power of 10, we wouldn't want to be expanding this. Anyway, we'll continue and differentiate in one more step. So x squared multiplied by itself 3 times, of course, is 6x to the power of 6. You can multiply your powers there as a shortcut. This is going to give us 3 multiplied by x to the 4 and then a minus 4. So let's say negative 12x to the power of 2 times 2, or 2 squared multiplied by itself. And then we'll have a 16 times 3, which is going to be a 48. It's our coefficient there, and we just have x squared. And then lastly, we have a minus 64. So now we can go ahead and find our derivative using our power rule, of course. So 6 comes down, subtract 1, and maybe we'll still do this in 2 steps. If you can avoid this, go for it. Sidestep the negative 12 or the subtract 12, and then differentiate x to the power 4, which is 4x cubed. Of course, you can bring that power down, multiply it by the existing coefficient to say a little bit more efficient way. And then we'll differentiate, sidestep the 48 and differentiate x squared. And then when we differentiate our minus 64, of course, that is a constant, so it's 0. And now here's our derivative, which of course, if that's all we wanted, we'd be finished. But that's not all we want. We want to look for a shortcut in case that power wasn't 3. Maybe it was 30. We wouldn't want to have to expand out and differentiate 31 terms. That's not anybody's idea of a good time. So minus 48x cubed, and then we'll have a 96x. So here's, we're at the stage now, I guess let's tinker around with this a little bit and see if we can look for a shortcut. And of course, it helps if you know what the shortcut is, so you might be kind of blindly following me here for a couple of steps. But I think first and foremost, removing a common factor is a good idea. And we can actually take definitely an x out, but also a 6 from each of those terms in our derivative. So this is going to be x to the power of 4. And of course, we'll have an 8 here, and that has to be a negative 8. That's going to drop down to an x squared. And then 6 times 16 is definitely 96, so this will be a plus 16. So nothing terribly fancy there, but just removing a common factor. Now if you recognize this x to the power of 4 minus 8x squared plus 16 as a quadratic form, then you can actually factor this. If you don't recognize it as a quadratic form, well then the thing you always look for, if you have a constant at the end, which we do here, 16, and if you recognize, if you square, maybe I'll highlight that, if you square this x squared term, you will actually get x to the power 4. So essentially what I'm recognizing here is I have x squared squared to get my first term. I have minus 8 times x squared, and I have plus 16. So I can just simply factor this, where instead of putting an x in both of my binomials, I'm putting an x squared. And again, if you're not comfortable with that, that's not something that you have to do quite often, but that's what we call a quadratic form in algebra. It's not just x squared as a first term and an x in the middle, it's actually x squared in the middle and x squared squared as our first term. So let's go ahead and factor that, and we are one step closer to maybe uncovering our shortcut. So 6x. So I guess what I'm suggesting here is we can factor this into two binomials, and there's going to be an x squared at the beginning of each of those binomials, of course, which is a degree higher than you're probably used to, but we're still going to factor it the same way. What adds to give me the middle number and multiplies to give me the outside numbers, which of course is going to be 16. And then we'll realize we need a pair of minus 4s. So this is going to be minus 4 and minus 4. So let's, of course, expand that out to make sure it's factored correctly, which is always a good idea. So we get x to the power 4, a minus 4x squared, another minus 4x squared. So I see we have our minus 8x squared term. And finally, a pair of minus 4's multiplied together gives us plus 16. So this is what our derivative actually looks like. So we got two more steps. First things first, recognize that we have x squared minus 4 multiplied by itself. And this is one of these moments again where if you know what the chain rule is, which I will share with you in a few more minutes, you can recognize why I'm manipulating this thing the way that I am. So if I factor and pull apart that 6x, I can say that's 3 times 2x, and I'm going to put my 2x at the end. Okay, so now that we have our derivative, let's compare it to our original function and see if we can recognize a shortcut instead of having to expand out the original function and rely on our power rule. So maybe to help you see the shortcut here a little bit, this power of 3 actually is dealt with in our derivative. And if you recognize, there seems to be a 3 out in front, and our power now on that x squared minus 4 function trapped inside seems to have gone down to 2. So that should seem like the power rule to you, hopefully, where the power comes down in front. And we subtract 1 from our power. So I think I will just rewrite those two numbers in blue to help you recognize that. So with that x squared minus 4 trapped inside this power of 3 function, or cubic function, we just differentiate the cubic function with that x squared minus 4 trapped inside. So the 3 comes down in front. Don't forget to subtract 1 from your existing power. So the question is, where does this come from? Where would we possibly get this 2x? And if you examine that trapped function, you can actually recognize that this 2x is actually the derivative of the trapped function. In that process of recognize that you have to chain two derivatives together via multiplication is a shortcut called the chain rule. Okay, so now let's formalize the chain rule a little bit better. And before we do that, to remind you of a composite function notation. If you have a composite function, f of g of x, it means precisely this, that the g of x function is inputted into the f of x function. And I kind of like to refer to the f as the outer function and the yellow g of x as the inner function, because the g of x is being inputted inside the f of x function. So here's the formal definition using function notation of the chain rule. So if you were going to differentiate a composite function, you first differentiate the outer function with the inner g of x still trapped. And to finish off the chain, you need a second link in your chain, and that's to multiply that first derivative by the derivative of the inside function. And a less formal way of stating that is to say, okay, if you're taking the derivative of a composite, make sure you differentiate the outer and then multiply by the derivative of the inner. But make sure you trap that inner function when in the first derivative, the derivative of the outer function. So let's look at one more example. See if we can follow through the chain rule. This one would be pretty tedious if we opted to expand this out with binomial expansion and get 13 terms, and differentiating 13 terms, that's a rather bad idea and probably error prone as well. So hopefully first of all you see a composite function. We have an inner and an outer function at work here, and of course the outer function is in white and the inner is in yellow. So the outer function is a power function, the power of 12. And I'm going to call that f of x, just to use, I guess, the formal definition, approach to the chain rule. And the inner function is this quartic polynomial, degree 4, x to the power 4 plus 5. So to do the chain rule, you essentially just differentiate both of those functions. You differentiate the outer and you differentiate the inner, but keep in mind we're not done of the outer function. We now have to take that f prime of x, that 12x to the power of 11, and we have to form a composite function. Basically input g of x into the derivative of the outer function. So take your 12x to the power of 11 and your input becomes the yellow g of x, x to the power 4 plus 5. So now to differentiate this function, y prime is going to be the derivative of the outer with the inner trapped multiplied by the derivative of the inner. So of course it's going to end up looking like this. So the y prime is going to be 12 times x to the power 4 plus 5, all to the power of 11, and don't forget to multiply by the derivative of the inside for x cubed.